Okay, our third speaker is Ethan Che, who is going to talk about robustly optimal auction design under mean constraints.
Hello. All right, thank you, everyone. So my name's Ethan, and today I'll be talking about robustly optimal auction design under mean constraints. So here we're going to revisit a very classical problem. So how do I sell an item to several potential buyers in order to maximize my expected revenue? And if I know the value distribution for each bidder exactly, and if I suppose in addition that they're IID, then this is a solved problem. I run a second price auction, and I set the reserve price to the virtual value. However, this requires some very sensitive information about the value distribution. And what typically happens in reality is that maybe the seller has some prior observations and has much greater confidence about a handful of summary statistics, such as the mean, median, variance, sample quantiles, etc. And there are really two sources of uncertainty that the seller faces. First, there's this distributional uncertainty. What does the distribution even look like? Does it have jumps, how smooth it is, etc. There's also uncertainty about the correlation structure. It's unclear for any instance which bidders want to participate and how their values are going to be correlated. So in order to model this scenario of a seller with a few pieces of information facing a lot of uncertainty, we're going to consider a revenue maximizing seller with n potential buyers with valuations in a known interval. And here we assume that the seller only knows the marginal mean values of each bidder. So they don't know the marginal distribution, they don't know the correlation structure. So we assume that bidders know their own values, but they also may have some arbitrary higher order beliefs about their opponents. So we want to find a mechanism that's both robust to the uncertainty in the valuation distribution and also the uncertainty in these beliefs. So in order to basically say whether a mechanism is robust or not, we're going to just talk about the revenue guarantee, which is the worst case expected revenue. That is, for any fixed mechanism, you just take the expected revenue, take the worst case over all feasible value distributions and all information structures. And we want to find the mechanism that achieves the highest such worst case expected revenue, which is solving for a saddle point. And as mentioned before, this can be modeled as a two-player game between the seller who picks a mechanism and nature who adversarially chooses a bidder environment. Oops. Know that if all bidders have the same marginal mean M is really the best possible revenue guarantee they can get because nature can simply set the values for all the bidders to be their mean exactly, and there's nothing really much the seller can do in that case. But this is a good scenario. So there's of course, a lot of prior work on robust auction design. I'm going to just address a handful of things. So of course, there's a work in the CS community on parametric auctions, but they're mostly interested in competitive ratios. There's a paper by Crosco. They basically solve the problem when there's one bidder, and they find basically the robustly optimal posted price. There's this paper by He and Lee, where they find the robustly optimal reserve price for a second price auction, but the bidders are identical and the marginal distributions are known. And then there's a paper by Brooks and Du. They find the robustly optimal mechanism, but they don't require that the valuations be private. And then there's two papers, one by Neiman and one by Brooks, and they will consider similar worst case distributions as the one I'm going to talk about to analyze properties of the second price auction. So here's the strategy. We're first going to restrict the set of mechanisms to be second price auctions. In that case, the only lever the seller can choose is the reserve price. So we're going to find this equilibrium between the reserve price and the worst case distribution. And the worst case distribution has a very intuitive structure. Nature is going to suppress competition. Nature is going to pick one bidder uniformly at random to be the highest value bidder, and the rest of the bidders, their values are going to be set to some fixed value alpha. And the highest bidder, their value is going to be drawn from a CDFH. So the information structure here is not important because we assume that bidders are not going to play their dominant strategies. But here the main information structure is going to be basically bidders know their own values, they know the distribution, but they don't know anything else. So visually, this worst case distribution has this kind of L shape. At any instance, only one bidder is the highest bidder, the rest are just going to be at alpha. And then here, the value distribution for the highest value bidder, it's going to take basically a Pareto distribution from alpha to 1. And actually, the mean constraints are enough to pin down what alpha is exactly. So what's a nice feature about this worst case distribution is that basically it makes the seller indifferent between all possible reserve prices. So if you imagine we're at a settle point, from the seller's perspective, the landscape is completely flat. But now we've only solved one part of the equilibrium. Now we have to find the reserve price G that actually makes this worst case distribution the worst case distribution. If the seller does something stupid, nature can actually do something much worse to punish them. So looking at things from nature's perspective, we can see that nature faces the following linear program. They want to choose a reserve price distribution F in order to minimize the expected revenue from the second price auction. And that's encoded by this phi function, which talks about the revenue of under the SPA, given a particular fixed values of value profiles. And we can see that's choosing this distribution subject to mean constraints and probability constraints. Because this is a linear program, we can use weak duality. And what does weak duality say here? Weak duality says that F star is going to solve the LP if and only if F star is feasible, and there exists an affine function L, which are basically the dual variables, such that L is always below phi, and the support of F star must be contained in the set in which L and phi intersect. So visually what's going on here is that the surface, this is going to be the phi function as a function of the value profiles, and this blue hyperplane, that's going to be our L. We can see that phi is above L everywhere. But on the point that they intersect, it's exactly on this L-shaped support for the worst case distribution. Now, why is this helpful? Because this gives us two constraints on phi, and thereby the reserve price distribution G. So it tells us that on the support, phi must scale linearly because it's equal to a linear function. Also, when you leave the support, this linear function pins down the derivatives of phi as you move away. So now, what is the reserve price that you get from this? You get a randomized reserve price. With some probability, you just set the reserve price at 0. You play a completely non-binding reserve price. With the remaining probability, you play a randomized reserve price from alpha to 1. And the worst case expected revenue that you get from here is going to be alpha. What's nice is that this is a very simple randomized reserve price rule that only requires a number of bidders, and this number alpha, which is calculated from the mean directly. And the simplicity makes it easier to adapt to complex settings. For example, if there's a context that's informative of the value distribution, for any realization of the context, you can use this auction, and all you need to know are the conditional expectations, which you can fit through regression. And now what's nice about this is that we can consider some large bidder asymptotics. What we can observe is that as the number of bidders grows large, the reserve price converges in probability to a completely non-binding reserve price. And this is because the environment is getting easier. The worst case distribution, F star, converges to a point mass on M. So we can see that as there are more bidders, nature loses the ability to suppress competition. We can now look at the gap between the best possible revenue guarantee, which is M, and the revenue guarantee that we actually get. And we see that the gap scales order 1 over n. And what's interesting is that there's this paper mentioned earlier by He and Lee. They basically find the same asymptotic, but they assume the seller has additional information. They know the marginal distribution exactly. Here, the seller doesn't have that knowledge, but we maintain the same asymptotic. Now, so we've pretty much solved everything when all of the means are the same, but in realistic settings, there's different bidders, or the seller may have a priori asymmetric information about the different bidders. 1 or 2 bidders may really dominate. But what's nice is that actually much of the same structure of the equilibrium is preserved. There's just a little wrinkle. And the wrinkle is that, well, if you're a bidder with a really, really low mean, you can't remember the structure of the worst case distribution. Basically, one bidder is chosen to be the highest bidder. The remaining bidders are set to alpha. If your mean is below alpha, then you can't be included. But the simple fix is that nature will just simply kick out all the bidders whose means are too low. And so the only differences are now that only the active bidders really participate. And the revenue guarantee is now, instead of being just fixed by the mean, it's going to be fixed by the mean of the means. And now we also have asymmetric selection probabilities. So before, nature picks each bidder uniformly at random to be the highest bidder. Here, the higher your mean is, the higher probability of being selected as the highest bidder. What we can see is that the reserve price distribution remains the same, except now we have fewer bidders, and this alpha number is different. And what's interesting is that even though all the bidders are ex-ante asymmetric, the seller still uses a symmetric reserve price. So in some sense, it gives a robustness explanation for the prevalence of symmetric and fair mechanisms. Note that the Meyerson optimal auction, potentially gives different bidders different reserve prices based on the virtual value. So now we might wonder, to what degree is this mechanism, is it good compared if you go outside the class of second price auctions? And what we're going to show is that this is going to be robustly optimal within a larger class of mechanisms we call competitive mechanisms. And what's the core of the definition of competitive mechanisms? It basically says if there's ever a situation in which I have a low value and your value is higher than mine, and we both know this with zero uncertainty, then I should never win. So in some sense, this captures mechanisms which utilize competition between the bidders in some kind of natural way. Note that these situations I'm talking about require there to be correlation in the value distributions. If, for example, I pick the lowest if values are IID and I pick the lowest value in the support, this definition has no binding in that situation because another bidder may not necessarily know that their value is higher than mine. And we can see that actually a first price auction without a reserve price or the common reserve price is a competitive mechanism. And sort of our final result is just to show that indeed we use a second price auction with this reserve price is robustly optimal among all competitive mechanisms. And what's nice is that this sort of very concretely, in this kind of robust setting, makes a comparison between different auction mechanisms beyond sort of DSIC mechanisms. And just to conclude, we first look at second price auctions, find the best reserve price, the worst case distribution, and then we use this to identify the effect of increased competition as the number of bidders grows large. We extend this to asymmetric bidders and find that a robustly optimal reserve price is still symmetric. And then we find that basically this auction mechanism is optimal within a wider class of Bayesian mechanisms. Okay, thank you.
You to repeat questions from the room because the microphone doesn't pick up very well. Okay. Is there one in the chat already? Or where did you point? No.
Oh, I thought we were waiting for.
Okay. Question from the room?
So, in a general mechanism, there could be multiple equilibria, and then the question is who is selecting the equilibrium? Even in the second price auction, it could have bad equilibria. So are you assuming that the designer chooses the best equilibrium always, or can the adversary choose an equilibrium?
So the question asks about whether equilibrium selection when there are multiple equilibria. And we assume here in that case that actually nature picks the equilibrium adversarially against the seller.
But then in the second price auction, wouldn't you have bad equilibria as well?
But we assume that bidders their values are private, and they never play undominated strategies.
Other questions in the room? Online?
I don't see any questions online. There was a discussion regarding the previous talk, but nothing regarding this talk.
So I have a question. So what if instead of knowing the mean, you get a sample, one sample from the distribution, or maybe multiple samples? Can you do something with that?
So no, this doesn't handle multiple samples. It only handles moment constraints. Although if you have different moments, like a second moment or something, then what's going to change is that for this duality argument, instead of having a hyperplane, you're going to have potentially a polynomial.
Okay, thanks again.